Okay, so again, this is AS1 Physics 1, January 2006, question 6. And the first part of the question asks to distinguish between resistance and resistivity. Okay. Now, first of all, resistance is the property of a conductor. Whereas resistivity is the property of a material. Resistance is measured in ohms. And resistivity is measured in ohm meters. Resistance is the opposition to current flow. Resistivity is caused by the arrangement of atoms. Okay. And if you look in the mark scheme, they were looking for 4 particular points, half marks for each, and then round down. So you really need to think about given all of those. So if you're distinguishing between resistance and resistivity, it's not just a one point. We're looking for resistivity is the property of the conductor, resistivity is the property of the material. Resistance measured in ohms, resistivity measured in ohm meters. Resistance is the opposition to current flow, resistivity is caused by the arrangement of atoms, depends on the atomic structure. Then the next part is state how the resistance and resistivity are related, define in all terms well. R equals rho L over A, where R is the resistance, again measured in ohms. Rho is the resistivity, and that's in ohm meters. L is the length in meters, and A is the cross-sectional area, and that's in meters squared. So R is the resistance, and that's equal to the resistivity times the length divided by the cross-sectional area. A length of pure wire and a negative temperature coefficient thermistor are heated in a temperature controlled environment from 0 to 100 degrees Celsius. On figure 6.1, sketch 2 graphs to show the variation of the resistance R of each of these devices with temperature theta. Label the graphs clearly with letters W for the wire and T for the thermistor. Okay, so this is looking at the relationship between resistance on one hand and temperature on the other. And what we know is that for a thermistor, the resistance decreases as the temperature increases, and it's something like so. Whereas for a wire, the resistance increases and it's a linear increase, but it does have a value at 0 degrees, and then it climbs steadily. So this will be W for the wire, and this will be T for the thermistor. On figures 6.2 and 6.3, sketch VI or IV characteristics to distinguish between ohmic and non-ohmic conductors. This comes up fairly often here, but an ohmic conductor, PD, is proportional to current, so that's a straight line through the origin. Probably better to use a ruler with that. And then we have, well, I against V for non-ohmic behavior could be anything, but if we do the thermistor that we had before, it's going to look something like that, but it's a curve rather than that. Ohmic conductor, well, that'll be a metal wire at constant temperature. Important to put that in because after the temperature changes, it's no longer ohmic. And the non-ohmic conductor, so with a metal wire for the constant temperature for the ohmic conductor, the non-ohmic conductor then will be anything from diode, filament bulb, thermistor. So any choice of any of those to go.